So, as I have said, today we'll be doing section 3.4, triple integrals in spherical coordinates. So, I assume that you have watched the associated lecture videos uploaded by the Institute of Mathematics in their YouTube account. Okay, so we will do maybe 4 examples involving triple integrals in spherical coordinates. So in here, of course, we will be able to tackle how to convert rectangular coordinates to spherical coordinates, but of course, in the form of integration problems, right? And then you will see in this slide here the formula, okay? Conversion of triple integrals from rectangular coordinates into a triple integrals in spherical coordinates. So looking at the formula in here, I just want to emphasize the following. So for this one, this actually gives us the conversion of the variable x, okay, to spherical coordinates. And then we have this guy, conversion of the variable y in spherical coordinates. And then finally, for this guy, let me use this. This guy here, it's the conversion of the z coordinate into spherical coordinate. And of course, this whole thing here, okay, this guy here, when we do the integration, this is your dv. Okay? So let us do this integration. We want to evaluate the triple integral, okay, over the ball B here. The function e raised to x squared plus y squared plus z squared raised to 3 halves dv, okay, where B it's the unit ball centered at the origin. Okay, so your B here, this is the set of all x, y, z in R3 such that x squared plus y squared plus z squared, okay, this is less than or equal to 1. Okay? And then aside from this conversion here, okay, aside from this conversion here, we can easily calculate the following conversion. We have x squared plus y squared plus z squared. This is equal to rho squared. Okay? And then we recall, we have tangent phi. This is equal to square root of x squared plus y squared over z. Okay? So we might use this later. Okay? And then, of course, we have the other in terms of theta. Okay? And then, in here, take note that, of course, your rho must be greater than or equal to 0. Your phi, this will be from 0 up to pi. And then the theta will be from 0 up to 2 pi. Okay? These are the possible range. Right? Your phi will run from 0 to pi. That's the maximum, up to pi. And then your theta will run from 0 to 2 pi. That's the maximum range. Okay? Now, in this particular example here, we have the triple integral over the ball B, okay, of e to the x squared plus y squared plus z squared raised to 3 halves dv with this conversions here. Okay? We will have the triple integral. Okay? Triple integral e raised to rho squared raised to 3 halves. Okay? So that becomes rho cube. Okay? And then the dv converts to rho squared sine phi d rho d theta d phi. Okay? Now, how do we choose the limits of integration for the triple integral? So, we are on the ball, okay? Centered at the origin. Okay? So, let me just draw partial ball here, partial part of the um, ball. So, in here, we will have our rho, okay? Our rho to run from the origin going to the roof of the ball. Okay? So our ball or our rho will run from the origin going to the roof of the ball. So our rho will be from 0 up to 1. Okay? Now, for the theta, okay, for the theta, this part here, once you have this radius, okay, once you have this, well, the ray, okay, once you have this ray, this will revolve, okay? Since you are considering the entire ball, okay, you have to rotate this ray here, okay, 360 degrees, which means that in here, our theta will run from 0 to 2 pi, okay? And then, again, since we are considering the complete ball, okay? So this is just this ball here, this is just on the first octant. But completely you cover all octants. Okay? Which means that our rho our phi, okay? Our phi will run from the positive z axis going to the negative z axis. Okay? From the positive z-axis going to the negative z-axis. And therefore, our phi will run from 0 to pi. Okay? So if we simplify this, we'll just have the integral 0 to pi, integral 0 to 2 pi, integral 0 to 1. Our integrand will be e to the rho cube. Okay? And then you have your rho squared here, which is nice because it will compensate this rho cube after, substitution. Okay? And then we have here your sine phi. And then you have your d rho, d theta, d phi. Okay? And then take note that we just have here constant limits of integration. Okay? And you know that if you only have constant limits of integration, you can actually separate each variable. Okay? You can separate each variable, meaning you can separate those with the rhos, okay? Join it with your d rho, the sine phi, just join it with your d phi, and then your t theta, you separate that. Okay? What I'm saying is, you can evaluate this integral into the following into the following form. You have your integral from 0 to pi of sine phi d phi, okay? Times you have the integral from 0 to 2 pi. That's for your theta. So you have your d theta in here. And then you have here the integral from 0 to 1 of e to the rho cubed rho squared d rho. You will get the same answer. Okay? So again, you can do this because the limits of integration, they are all constants only. You cannot do this if you have limits of integration which are functions, non-constant functions. Okay? Questions so far? Therefore, we evaluate this. This is what? For this one, you will have negative cosine phi evaluated from 0 to pi. And then here you have integral 0 to 2 pi of d theta. Just write it as 2 pi. And then for this guy, you do your substitution, u equals what? Say rho cube d u, this is equal to 3 rho squared d rho. Okay? And you will have 1/3. Okay? You will have 1/3 integral e to the u, 1/3. So 1/3 integral e to the u du. Okay? And in here, if rho is equal to 0, u will also be equal to 0. And if rho is equal to 1, u is still 1. Okay? Therefore, we will have, so we evaluate this, we have 2 pi over 3 times, for this guy, negative cosine phi, evaluated at pi, that's negative 1. So you will have 1 in here, okay? And then minus negative, so this becomes plus cosine 0, that's 1, okay? And then for the last guy here, you have e to the 1 minus e to the 0. Okay? Or if you want to simplify this, this is just 4 pi over 3 times e minus 1. So this is the integral. Okay? Questions? Okay. Let's go to our next problem here. So we want to evaluate triple integral over e of z dv, where e lies between the spheres x squared plus y squared equals x squared plus y squared plus z squared equals 1, and x squared plus y squared plus z squared equals 4 in the first octant. Okay? So let's try to sketch. So we have this. Since we are only going to do first octant, okay? Let's just have this part. This guy here, it's a sphere of radius 1, while this guy here, it's a sphere of radius 2. So in here, we have, say, this is 1, this is 1, this is 1. So your sphere will be something like this, or at least that portion of the sphere that we need, something like this. Okay? And then for the one with radius 2, say this is 2, this is 2, this is 2 here. So this is the portion of that sphere. So we want the solid in between these two portions of spheres. Okay? So this guy, again, this guy here, this is x squared plus y squared plus z squared equals 4. Or simply, this is equivalent to rho equals 2. Okay? And then for this guy here, we have x squared plus y squared plus z squared equals 1. Or simply, this is equal to rho, or this is equivalent to rho equals 1. Okay? So which means if we get the ray, okay, that will run over that solid. So starting from the origin, we have this, and then we have this part here. Okay? So this is from rho equals 1 up to rho equals 2. Okay? For the phi, so you have this phi here, okay? But we only need up to first octant, okay? So meaning it will not go below the xy plane. So the phi will only be up to this part. Okay? So phi, that's your phi. This is your rho. And then for the theta, okay? For the theta, let me use this color here. For the theta, you have from, so we have counterclockwise from the positive y, okay? Or counterclockwise from the positive x, okay? So you have this, okay? So you have this ray here, and then it will only run towards that. And that's just pi over 2. So this is your theta. And my apologies, this is this guy here. This is your phi. Okay? Therefore, what do we have? How do we convert this? So we have the triple integral over e of z dv. This will be integral, okay? The triple integral. Again, your z becomes this guy here. So that's rho cosine phi. Rho cosine phi. The dv converts to rho squared sine phi. And then we have your d rho d theta d phi. Okay? Again, your rho will run from 1 up to 2. Your theta will run from 0 to pi over 2. And your phi will also run from 0 up to pi over 2. Okay? And just like the previous example, all the limits of integration here, they are all constants. So you can separate each variable. Okay? So this guy here, you can write as the integral from 0 up to pi over 2. So the outer integral here, it refers to your variable phi. So let's write cosine phi sine phi d phi. And then you have the integral from 0 to pi over 2. That refers to your theta. There's no theta in the integrand in here. So this is just the theta. And then you have the innermost integral. That's for the rho. That's the integral from 1 up to 2. And you have here rho cube, the rho. Okay? Then you can integrate this. For this guy here, you multiply and divide by 2. And you will have 1/2 integral 0 to pi over 2 of sine 2 phi d phi. That will be easier to integrate. For the theta part, this is just pi over 2 minus 0. So that's just pi over 2. And then for the rho part, you have rho to the 4 over 4 evaluated from 0 up from 1 up to 2. Okay? And then this guy here, if we integrate, you will have negative cosine 2 phi. Then we'll have over 4. Then you evaluate this from 0 until pi over 2. Then you still have your pi over 2 there. And in here, you will have what? Rho to the 4 over 4. I mean, 2 to the 4 over 4. That's just 4. Then we have minus 1/4. Okay? And then evaluating, at pi over 2, you have negative cosine of 2 times pi over 2. So that's negative of negative 1. So that becomes 1/4. And then minus negative of cosine 0. So that becomes plus 1. And then we still have the denominator 4. Then in here, you have pi over 4. And then in here, lastly, let's just put this into fraction form. We'll have 17 over, sorry, not 17, but 15 over 4. Okay? And all in all, what do we get? 2 times 4, that's 8 times 4, that's 32. So we will have 15 pi over 32. Okay? Questions? Okay, so hindi po ba pi over 2? Saan yung pi over 2? Ah, yeah, you are correct. Yeah. This guy here, this is pi over 2, not pi over 4. Thank you. So pi over 2. So this guy here, it's just over 16. Thank you for noticing that. Okay. Okay. Other questions or corrections? Okay, so move to our next example here. So we want to evaluate integral from 0 to 3, integral from 0 to square root of 9 minus y squared, integral from square root of x squared plus y squared up to square root of 18 minus x squared minus y squared of x squared plus y squared plus z squared dz dx dy. Okay? So we want to evaluate this. So first, let us analyze. For the innermost integral, that's for the variable z. So you will have z equals square root of x squared plus y squared to z equals square root of 18 minus x squared plus y or minus y squared. Okay? Now, this guy here, what's this? This is a portion of an elliptic cone. Is it an elliptic cone? You have your z squared equals x squared plus y squared. What is that? So this portion here, you have z squared equals x squared plus y squared. So you will have, yeah, this is an elliptic cone. That's just portion of an elliptic cone. Okay. So that's a portion of an elliptic cone. Your z is positive. Okay. Your z is positive. So you are only taking the upper part of the elliptic cone. And then for this guy here, this looks like sphere. So portion of the sphere. Okay. So if you check this, this is your z squared equals 18 minus x squared plus y, minus y squared. So you will have x squared plus y squared plus z squared equals 18. So that's the portion of, that's a portion of the sphere. Okay. So if we have that, okay, if we try to sketch these two guys here, okay, if we try to sketch these two guys here, so we will have the following. So portion of the cone, upper part only. So maybe you have something like this. You have something like this. Okay, and then of course you have the circular part in here. Okay, and then this part here, okay, this part here, part of a sphere, okay, part of a sphere. So suppose this is of radius square root of 18. That's 3 square root of 2. So say this is that part, okay? This part here, okay? So you will have this, okay? So you want your Z to run from the portion of the cone until to that portion of the sphere, okay? So in here, this is that portion of the sphere. This is that portion of the sphere. It means that you have the roof as, you have the sphere as the roof of your solid. Okay? So you want your Z to run from the portion of the sphere until to the from portion of the cone until the portion of your sphere. Okay? Okay? So we have that. Okay? But let's try to do the conversion. Let's try to do the conversion. Remember that your Z is something like this. Okay? Or yeah, let's check everything first. Let's check everything first. So you have that for your Z. For the X, we have x equals 0 to x equals square root of 9 minus y squared. And clearly this guy here, okay, this guy here is just circle of radius 3. So x squared plus y squared equals 9. Okay? So your x, okay, your x will run from x equals 0 until x equals 3. Okay? So x equals 0 until x equals 3. So you will have this portion from this point here. Let me use a different color. So from this point here, going to that. Okay? That's the maximum. That's the maximum value for your x. From 0 until that portion of the circle, which is of radius 3. So you have this up to that point. Okay? And in here, your y runs from 0 to 3, which means you will cover entirely the whole part of the disk there. Okay? So your y is from 0 up to 3. Okay? So try to imagine our the solid we are considering here, or the region we are considering here. In terms of the spherical coordinates, what do we have? Okay, what will we get in here? In terms of the spherical coordinates, okay, of course, your rho will run from the origin going to the roof. But the roof, it's your sphere. Correct? So your roof is that sphere. So your rho, okay, your rho will run from 0 until square root of 18. That's the radius of the sphere. Okay? And then let's talk about phi first. Your phi will be running from the positive z-axis going to this side here, to this wall. Wall, it's just this cone in here. This cone in here. So from the positive z-axis going to that wall. Okay? Okay? And then, combining these facts in here, okay, it is implied that you are only considering the first octant. You are only considering the first octant, and therefore, you're just doing this part in here. So it will be your theta, okay? The theta will just run from this positive x-axis going to the positive y-axis only. So this is your theta. Your phi, again, your phi will be from this up to this. Okay? So let's write theta first. Theta will be from 0 to pi over 2. For the phi, of course, it will start from 0. The ending is this part in here. But this guy here, this part here, we can use the conversion tangent phi. Okay? we can use the conversion tangent phi equals square root of x squared plus y squared over z. But our z, that's the portion of our cone. Our z is square root of x squared plus y squared also. So this is equal to 1. Which means, particularly this part here is just theta equals pi over 4. So our, sorry, not theta, but phi equals pi over 4. So our phi will run from 0 until pi over 4. Okay? So in here, okay, we'll convert this into spherical coordinates. Of course, x squared plus y squared plus z squared, that's rho squared. Okay? And then the dv, or this dz dx dy, it's equal to rho squared sine phi. In here, I'll write d rho d theta d phi. Okay? And again, our rho will run from 0 up to square root of 18. Our theta will run from 0 up to pi over 2. Phi will run from 0 until pi over 4. Happy? So, what's left to do is to evaluate. So again, constants here. So we can separate. We have the integral from 0 to pi over 4. We have the d phi. So we have here sine phi, d phi. And then integral from 0 to pi over 2. We have d theta. So this is just d theta. And then integral from 0 to square root of 18. We have rho. So here we have rho to the 4 d rho. So evaluating, we have negative sine phi evaluated from, negative cosine phi. So negative cosine phi evaluated from 0 to pi over 4 times, we have pi over 2 again in here. Then times, we have rho to the 5 over 5 evaluated from 0 to square root of 18. So evaluating, we will have here negative cosine pi over 4. That's negative square root of 2 over 2 minus negative cosine 0. So that's plus 1. Then we have here pi over 2. Then in here, we will have fifth power of square root of 18. And what is that? So square root of 18, that's 3 square root of 2. Anyway, let's just write this as square root of 18 raised to 5 over 5. So this will be the value of that triple integral. Okay? Questions? So in here, the crucial part, it's the conversion of this guy here into your spherical coordinates. Okay? Questions? All right. Finally, let's have this last example. Use spherical coordinates to find the volume of the solid that lies above the cone. Z equals square root of x squared plus y squared. So we have the cone earlier. And below the sphere, x squared plus y squared plus z squared equals z. Okay? X squared plus y squared plus z squared equals z. So you have the sphere. Okay, you have the sphere here, part of the sphere actually, and then you have the cone. So it's like, you know, you have your ice cream with the cone and your ice cream on top. So again, crucial part in here is to convert. But all the data are here, right? All the data are here. Okay. So how do we do this? Of course, volume of the solid, it means your function is 1. Okay. So you will have this guy here, integral over that solid S dv. Okay. So the main problem is what are the limits of integration. So this is very similar to what we have earlier. Okay. So in here, we clearly see for the phi part, okay, for the phi part, it's from the positive z axis going to the part of the cone. Okay. So our phi will be from 0 to pi over 4. Okay. And then, since we are considering everything, okay, we are considering everything in here, okay, all the part here in the solid, all throughout, our theta will run completely 1 revolution, which means the theta will run from 0 to 2 pi. Okay. On the other hand, what about our rho? Of course, our rho will run from where up to where. So you will have this part here. This is the lowest point. The highest point will be the roof. And that's your sphere. Okay? So we need to convert this sphere here. Okay? And to convert that, how do we write this? Take note that this guy here, this is equal to rho squared. On the other hand, your z is this guy here. That's rho cosine p. So there is a question. Paano po naging ganun ang graph ng sphere sa figure kung ang center po niya ay origin with radius square root of z? It's not centered at the origin. Look at this. Okay, look at this. You have your x squared plus y squared plus z squared equals z. You bring this to the other side. You will have x squared plus y squared plus z squared minus z equals 0, correct? And then you complete the square for the z part. Add 1/4. So 1/4 here, 1/4 here. And this guy here, z squared minus z plus 1/4 that's actually what? Z minus 1/2 quantity squared. So this guy here, it's Z, it's x squared plus y squared plus Z minus 1/2 quantity squared equals 1/4. You actually have a sphere centered at 0, 0, 1/2, radius 1/2. That's why, as you can see in here, you have the 0, 0, 1 there. You have the origin here. Okay? Okay? All right. So that's why the sphere is actually on top of your xy plane. Okay? All right. So now, going back to this computation, as I have said, this guy here, that's your rho squared. And of course, your z, it's rho cosine phi. So if we calculate this, you will have rho squared minus rho cosine phi equals 0. Then you can factor out rho. You will have your rho times rho minus cosine phi equals 0. This guy here, rho equals 0. That's the origin. The sphere part, it's this guy. Rho minus cosine phi equals 0. Okay? Rho minus cosine phi equals 0. So this guy here, okay? This guy here, oops. This guy here will take the equation rho equals cosine phi. Okay? Okay? So your rho will run from 0 to cosine phi. Okay? Therefore, we will have the integral here, integral. And then you have your dv, that's rho squared sine phi d rho d theta d phi. As I have said, your rho will run from 0 up to cosine phi. Hello? And then your theta will run from 0 to 2 pi, and your phi will run from 0 to pi over 4. So in this case, we cannot separate somehow because in here, you have a non-constant upper limit of integration. So let's evaluate first. Anyway, evaluation with respect to rho, since you just have a polynomial here, you take your sine phi as constant in here, evaluation will be easy. So this guy here will be the integral from 0 to pi over 4, integral from 0 to 2 pi, and then you will have your rho cubed over 3, evaluated from 0 to cosine phi. Then you will have your sine phi d theta d phi. So you will have your 1/3 integral from 0 to pi over 4, integral from 0 to 2 pi, and you have your cosine cube phi sine phi, and then you have your d theta d phi. At this point, you can separate. You can separate the two variables here because, the limits of integration, they are just constants. Okay? So let's separate them. You have your 1/3 integral from 0 to pi over 4. You have your cosine cube phi sine phi d phi. And then you have your 0 to 2 pi or integral from 0 to 2 pi d theta. So for this, you can just let u be equal to cosine phi du, this is negative sine phi d phi. Okay? So in here, we will have 1/3. Okay? You have some integral in here. And you will have u cubed. You actually have negative. So I'll put the negative outside. So you will have u cubed du. And then integral from 0 to 2 pi d theta, you just have 2 pi. So if u is equal to theta, if phi is equal to 0, you have 1 in here. If phi is equal to pi over 4, that's square root of 2 over 2. Okay? Therefore, you will have negative 2 pi over 3 times u to the 4 over 4 evaluated from 1 up to, I'll just put 1 over square root of 2. That's square root of 2 over 2. So this guy here is equal to negative 2 pi over 3 times 1 over square root of 2 to the 4th power. That's 1/4. Then minus 1 in here. I'll put the denominator 4 together with this. So I'll have 1 over 12 in here. Okay? So if we simplify this guy here, 1/4 minus 1, that's negative 3/4. So we will have 2 pi, or we have pi over 6. Okay? Pi over 6 times 3/4. So this is equal to pi over 8. So that's the volume of that solid.